So let us begin today's lecture. So let's try and recall, okay, what we are trying to do, right? So the goal of this part of this course, which is simplicial homology, is to count the number of holes of different dimensions. Okay, so we have been given some simplicial complex, and our goal is to count the number of holes of different dimensions. So what we have done so far, right? So in order to undertake this study, okay, we first define these different vector spaces for for every integer p. So we have a vector space c minus 2, we have a vector space c minus 1, we have a vector space c0, c1, c2, and so on, right? So this is what we did 2 lectures back. In the last lecture, okay, we went ahead and defined these boundary operators. Is this okay? So you can see that the boundary operator between c0 and c minus 1. Okay, there are 2 boundary operators that are mentioned here. The first is daba 0 and the second is epsilon. Okay, so this is the notation that we will be following. Okay, whenever I write daba 0, I mean, I will implicitly mean that we are working with the usual homology. Okay, which recall means that we will be setting c minus 1 to be the trivial vector space, and we will be defining daba 0 the way we defined yesterday, right? On the other hand, when I write epsilon, okay, so it means that we are working with the reduced homology, which means that c minus 1 we will set it to be c minus 1 we will set it to be the z2, and we will define daba 0 accordingly, right? So this notation epsilon means that we are working with reduced homology, and the notation daba 0 means that we are working with the usual homology. Okay, so typically I'll be only writing either daba 0 or epsilon, okay, not both, but here since I want to talk about them jointly, I have written daba 0 slash epsilon, right? So just to summarize, this is what we have done, right? So we have defined Cp, which is a vector space for every integer p, right? So this is what we have done. Then we defined this daba p, which is the boundary operator, and we also saw that this is a vector space homomorphism, and between c0 and c minus 1, sometimes we will use daba 0 or epsilon to imply that we are either working with the usual homology or the reduced homology, right? So last time we also saw a bunch of examples to sort of try and appreciate the significance of this daba p operator, and we saw that this kernel of daba p, right? So kernel of daba p, so recall that daba p is a linear operator. So this kernel of daba p, so daba p, let's say, goes from so daba p, okay, goes from cp to cp minus 1, right? And kernel of daba p is all those p chains in cp such that daba p maps them to 0, right? So we saw that this kernel of daba p contains useful information from the perspective of homology. In particular, if we saw that, let's say we have such a simplicial complex, right? So if you give 1 2 plus 2 3 plus 3 4 plus 1 4, right? So if you give this as input to daba 1, the output as you must have guessed, will be 1 plus 2 plus 2 plus 3 plus 3 plus 4 plus 1 plus 4, and this will be 0. So you can see that this boundary operator takes these p chains which intuitively look like cycles, and those that enclose these hollow regions, okay, so those cycles are taken to 0, right? So from that perspective, this kernel of daba p indeed contains useful information from the perspective of homology. Okay, so let me pause here for a second or two. If you have any questions with regards to this summary, this may be a good time to ask. Alright, so I don't see any raised hands, so maybe we can advance. Okay, so indeed this daba p is very useful for us, right? However, there are some issues with daba p, okay, and I noticed that some of you realize that daba p is, while it is good, but there are some issues, right? So let's just try and go over some of the issues with this daba p operator. Okay, so let's try to ask, okay, so this is a very trivial simplicial complex in the sense that it has only one two-dimensional hole, right? So in that sense, this is very, very, this is a very simple example. So let's look at a slightly complicated example. Okay, in particular, let's look at this example, right? So this is a simplicial complex. Of course, this is a graph. So as you may have realized by now that the graph is one of the simplest simplicial complexes, right? So this simplicial complex, as you can see, has 4 vertices, 1, 2, 3, and 4. So there are 4 vertices, and as you can see, there are 5 edges. Okay, so that's it, right? So if I sort of intuitively asked you, okay, can you take a guess how many holes are there in this simplicial complex, right? So if you had to take a guess, then perhaps you would say, look, here is one hole, right? So here is one hole. So this is the first 2-dimensional hole, and here is another hole. So maybe the second 2-dimensional hole, right? So if I asked you to take a guess, right, then clearly your guess may have been, 2. Right, so let's see, what are the different elements in the kernel of DABA1 for this simplicial complex. Okay, so let's try to see. So first, let's try to formally define this simplicial complex. So as I said, it has these 4 vertices, right, and it has these 5 edges, right. So again, I would like to emphasize that I am being a bit sloppy here. Okay, ideally I should write 1, 2, and similarly this I should write as 1, 2, and so on. Okay, but I don't want to sort of unnecessarily put in too many symbols and unnecessarily complicate things. Okay, that's the reason I am writing it in this fashion. Is this okay? Okay, so in your assignments also you can write it in this fashion. However, you should be clear what is happening. Okay, those don't just blindly write certain things. Okay, so as mathematicians, sometimes we try to be sloppy to avoid too many symbols. But whenever there is a need to be a bit rigorous, like for example, let's say you are going to talk with someone outside this course, or maybe you want to talk with some mathematician, who is living in some some other part of the world, right? So you can't just say 1, 2, 1, 3, and so on. First, you will have to tell him what do you mean by 1, 2, what do you mean by 1, 3, and so on and so forth. But for this class, it's we will write it this way, and you can also continue writing it this way. But I hope you are able to see why am I doing this and what it is actually supposed to mean. All right. So this is the simplicial complex under consideration. So let us look at these different one chains. Right, so this is a one chain because you can see that I have taken one-dimensional face, I have taken another one-dimensional face, and I have taken another one-dimensional face, and as you can see, I have taken their formal sums. Right, so you can see that here there are 5 edges. So if you remember what this C1 was made up of, so this was made up of summation AI, okay, sigma I, where AI belongs to Z2, right, and this sigma I belongs to F1 of delta. Right, so here F1 of delta includes 5 edges. So I hope you agree that 1, 2 plus 1, 3 plus 2, 3, right? This can be viewed as I should maybe write it properly, 1, 1, 2 plus 1, 1, 3 plus 1, 2, 3 plus 0, 2, 4 plus 0, 3, 4. Okay, so these, so maybe I'll use a different colors for these coefficients so that it is clear what I'm talking about. Okay, so these are the coefficients, so 1, 1, 1, and these are your different faces. Okay, so these are your different faces. So I hope it is clear that when I write 1, 2 plus 1, 3 plus 2, 3, I actually mean this formal sum. Okay, so again, I am being a bit sloppy here by not explicitly mentioning what are the coefficients of these different faces. But again, you can see that while I am being sloppy, okay, you can unambiguously decipher it as representing this one chain over here. All right, so far so good. So let's take this one chain and apply this DABA1 operator. Right, so it is easy to see that if I apply this DABA1 operator, okay, I'll end up with 1 plus 2 plus 1 plus 3 plus 2 plus 3, and everything will cancel off, and I hope you agree that we will end up with this 0 over here. Right, so again, I would like to emphasize what is this 0 over here. This 0 is the additive identity that is there in this C0 vector space, which means that this is, so as you can see in the above simplicial complex, there are 4 vertices. So 0 means this is 0 V1. So maybe I'll use 0 plus 0 plus 0 plus 0, and maybe I'll use this blue to represent the different vertices. So 0, 1, 0, 2 plus 0, 3 plus 0, 4. Right. So when I write 0 over here, I actually mean, Okay, when I write 0 over here, I actually mean the additive identity of this C0 vector space, and this 0 has to be interpreted in this form, that this is the 0 chain, okay, where all the coefficients are taken to be 0. Okay, so in that sense, you can see that DABA 1, when it is applied on this one chain, we get the answer to be 0, right? So you can see that this one chain corresponds to this three faces over here, these three edges over here. Now let's look at this one chain, right? So this is 2 3 3 4 and 2 4, right? So you take these collection of edges, right, and you use that as the input to this DABA1 operator. So by a similar analysis, you can see that the output of this will also be 0. Okay, so far so good. Now how about this one chain, right? So you give 1 2 2 4 3 4 and 1 3, right? So you give this as input to the DABA1 operator, and you will again see that the output is 0, right? And similarly, you can see that if you give 0 as input to DABA1, then the output will be 0. So let me again emphasize what do I mean over here. See, although I write 0 here and 0 here, I hope you agree that these are not one and the same things, right? The 0 on the left is the additive identity of C1, whereas the 0 on the right is the additive identity of C0. Okay, so the 0 on the left is sorry, it should be 0 0 0 0 0. Sorry, I should give some space in between. So it should be 0 0 0 0 0, and it should be 1 2 plus 1 3 plus 2 3 plus 0 2 4 plus 0 3 4. Okay, so this is the 0 that is there over here. So this is actually a one chain, right? The 0 on the left is the one chain, whereas the 0 on the right is the to distinguish this, right? So anyways, let's just summarize what happened. Okay, so we wanted to ask what are the issues with this DABA P operator. So we focused on this simplicial complex as an example, right? And we looked at what are the different elements in the kernel of DABA 1, right? So you can see that by a trivial calculation, we saw that at least there are 4 elements in the kernel of DABA 1, right? So kernel of DABA is the collection of all those one chains, okay, which are taken to 0. So you can see that on the right hand side, the output is always 0, right? So that's why all these elements definitely belong in the kernel of DABA 1, right? So as I said, at a level of intuition, one may believe that this simplicial complex over here has two-dimensional holes, right? So the first is over here and the second is over here. However, if you sort of directly count the number of elements in kernel of DABA 1, clearly it has more than 2 elements. Right, so if you want to count the number of holes in this simplicial complex, you cannot do a simple counting of the elements in kernel of DABA 1. That is the first issue. Okay, let me again summarize. Our goal was to count the holes in this simplicial complex, right? One cannot, as a means to, answer this question, like how many holes are there, one cannot simply count the number of elements in the kernel of DABA 1, right? So while kernel of DABA 1 does include useful information, you cannot blindly count the number of elements. That's the summary. Okay, so let me pause over here for a second or two. If you have any questions with regards to the discussion that we just had, please ask. All right, so I don't see any raised hands. Okay, so this was one of the issues with this DABA P operator, right? So although I gave the example in the context of DABA 1, I hope you will be able to extend this example to other, DABA P operators as well. All right. So the next issue with DABA P is that, DABA P cannot distinguish between a filled hole. Okay, so let me put it in quotes here. Okay, because this filled and empty, these are by themselves they don't have any meaning. We are sort of attaching some meaning to what a filled hole means and what an empty hole means. So here is an example. of what intuitively I mean by that. Okay, so of course there will be a formal interpretation soon of what a hole means and so on and so forth. At this point, we don't know what a hole is, right? We are sort of having some intuitive guess of what a hole should be. Okay, but slowly we are moving towards giving a formal description of what a hole exactly means. Okay, what a filled hole means, what an empty hole means, and so on. At this point, everything is at a level of intuition. We are trying to put in the definition that tries to capture our intuition. Okay, so nevertheless, let's work with this whatever interpretation you have of a filled hole and an empty hole. So here are two examples in that context. So here is a simplicial complex, here is a simplicial complex. Okay, so the simplicial complex on the left has three vertices, 1, 2 and 3, and it has three edges, right? So it has three edges. On the other hand, for the graph or the simplicial complex on the, sorry, I shouldn't say graph, it's indeed a simplicial complex. For the simplicial complex on the right, you have three vertices, 1, 2 and 3. You have three edges. In addition, you have this triangle, right? So that is the difference between the simplicial complex on the right and the simplicial complex on the left. So intuitively, if I asked you if there is a hole in the simplicial complex on the right, on the left, your answer would be yes, here is that simplicial complex. Right? So, and if I ask the same question in the context of the simplicial complex on the right, you will say no, there are no holes. While there are these one chains that enclose some region, that region is filled by this triangle. Right? So because of that region, this region is filled. Right? So there are no holes in here. Right? So let's see if kernel of DABA1 is able to distinguish between these two cases. Right? At a level of intuition, we agree that this simplicial complex as a whole, whereas this simplicial complex doesn't have a two-dimensional hole. So what we are now trying to do is we are trying to verify or check if kernel of DABA1 is able to distinguish between these two cases, right? So so recall that this DABA1, right? So this DABA1 is a function, okay, that goes from C1 to C0, right? So in order to understand what this DABA1 is, let's first try to understand what C1 is and what C0 is, right, in both these cases. So let's try to understand what C0 is. So C0, as you recall, is the collection of all zero chains, right? So let's try to write down the zero chains for the simplicial complex on the left. So the first zero chain is 0. The second zero chain is 1, 2, 3. You have 1 plus 2, 1 plus 3, 2 plus 3 and 1 plus 2 plus 3. Okay, so as you can see, these are the different zero chains for the simplicial complex on the left. Okay, but a careful observation will tell you that, well, for the simplicial complex on the right, the vertices are the same, right? So since the vertices are the same, the set of this zero chains for that simplicial complex will also be this itself. Right. So similarly, since the set of edges for the simplicial complex on the left and the set of edges for the simplicial complex on the right, since they are one and the same, the vector space of one chains, which is C1, this will also be the same, right? So here it will include the first will be the 0, 1 chain, then there will be the one chain which is 1, 2, then you have 1, 3, then you have 2, 3, then you have 1, 2 plus 1, 3, 1, 2 plus 2, 3, and so on. Is this okay? So the point you have to appreciate at this point is that although this simplicial complex has a two-dimensional face, the presence or absence of this two-dimensional face doesn't affect the definition of C0 and C1 in either of these cases. Okay, so that is what I would like you to appreciate. If you are able to appreciate that, then it should be clear that since DABA1, okay, since DABA1 only depends on C1 and C0, it indeed must be the case that if you take this one chain, that is 1, 2 plus 1, 3 plus 2, 3, which is this one chain over here or this one chain over here. In either case, if you give this one chain as input to DABA1, the output will be 0. Right? So you can see that the kernel of DABA P, so here in this example we looked at kernel of DABA1, but in general, if you want to, if you sort of extended this definition or extended this example, you will be able to, conclude that in general, the kernel of DABA P could either represent hollow P cycles or they could represent filled P cycles. Right? So if you just look at the elements of kernel of DABA P, you would not be able to conclude whether the elements there indeed represent these holes that we are interested in, or they represent like pseudo holes. So by pseudo holes I mean those cycles which are filled, right? So we won't be able to just look at the kernel and conclude that. Okay, so I hope you are able to appreciate the difference. I hope you are able to appreciate the different issues that are there with this Daba P operator. Is this okay? So on one hand, we saw that kernel of Daba P includes interesting information for us from the perspective of homology, but you cannot just count the elements and conclude that, oh, there are so many holes. And even if there are more than one element in this kernel of Daba P, you cannot conclude that indeed the original simplicial complex must have some P plus one dimensional holes. Because although the kernel may have several elements, it is possible that they represent these pseudo holes in the way I defined a few minutes back. So let me pause here for a second or two. If you have any questions with regards to what we just discussed, this may be a good place to ask. Are there any questions? All right. So I don't see any raised hand. So maybe we can advance. All right. So I hope the story so far is clear. Our goal was to count the number of holes. In that direction, we defined these different vector spaces. We defined these different boundary operators, which were, as we saw, were also vector space homomorphism. Sorry, not isomorphism. Vector space homomorphism. And we saw that these boundary operators were called boundary operators because you took a face to its boundary, right? Like let's say this is a triangle. If I gave this as input to the Daba2 operator, it will give me 1 2 plus 1 3 plus 2 3, right? So this will be the output of this face 1 2 3 over here. So as you can see, if you give two face, the output is the one chain that represents the boundary of this two-dimensional face. So because of this reason, this Daba2 is referred to, or in general this Daba P is referred to as the boundary operator. And we also saw that this is a vector space homomorphism, and we saw that it is useful because the kernel, its kernel contains useful information, right? However, we realize that we cannot just blindly count the elements in the kernel of this operator. So we have to do something smart. In particular, we have to count things so that the above issues are taken care of. Is this okay? So this is what we are going to do. So in particular, our goal now is to make sure we count the elements in this kernel of Daba P in a careful way. Okay, how do we do that is what is going to be the point of discussion. Okay, so the first thing is this genius observation, right? So on one hand, this is something you already know. Nevertheless, it is genius because although you may know that such a thing exists, you will see the way it is now used to make sure the above issues are taken care of, right? So what is the genius observation? Okay, so let's go back to that example that we had above. So that we had a simplicial complex and we had another simplicial complex. So both of them had the same number of vertices and same number of edges, right? So maybe I'll draw it properly. Okay, and here I will also draw it properly. Okay, so there are 3 vertices and 3 edges, but the difference for the simplicial complex on the right is that we have an additional triangle here, right? So in both cases, right, as we saw, so let's label this. So let's say this is 1 2 3, this is also 1 2 3. So in either case, the kernel of Daba 1, okay, so this includes. So if you sort of write down the kernel of Daba 1, it will include 0 and it will include 1 2 plus 1 3 plus 2 3. Okay, so if you sort of try to write down the different one chains, okay, which Daba 1 will take to 0, you will see that this is one chain which will be taken to 0 and this is another one chain which will be taken to 0. So these will be the different elements in kernel of Daba 1. Right, but the issue is that the kernel of Daba 1 will be the same whether you are looking at this simplicial complex or this simplicial complex. Okay, so that is what the issue is, right? So the brilliant or the genius observation over here is that this one chain, okay, which is the cause for concern for us. Okay, so this is a cause for concern because on the for the simplicial complex on the left, this indeed represents in some sense the boundary of a two-dimensional hole, whereas here in this simplicial complex, this represents the boundary of a filled hole, right? So we would like to be able to distinguish when this represents a hollow region and when this represents a filled region, right? So the genius observation is that this one chain, okay, so this one chain is the boundary of this face 1, 2, 3, right? So observe that in this figure you don't have this triangle, right? So let me again repeat. In this figure, this one chain, okay, cannot be the boundary of 1, 2, 3 because there is no triangle 1, 2, 3 present. In other words, this one chain for the figure on the left does not belong to the image of Daba 2. Okay, for the figure on the left. Whereas for the figure on the right, indeed, this belongs to the image of Daba 2. Okay, so here is what is happening, right? Just by looking at the kernel, we weren't able to figure out whether this, okay, so just by looking at the figure, just by looking at the kernel, we were not able to conclude whether this one chain represents a hollow region or a filled region. However, we noticed that for the figure on the left or the simplicial complex on the left, this one chain does not belong to the image of Daba 2. Why does it not belong to the image of Daba 2? So what is C2 for the figure on the left? So I hope you agree that since there are no triangular faces, C2 is the trivial vector space, right? So which means that Daba 2 will take this 0 and map it to 0. So this 0 on the left is an element of C2, whereas this 0 on the right is an element of C1. Is this okay? Right? For the image on the left, I hope you agree that image of Daba 2 is simply the 0, 0, 1 chain, right? So this is the 0, 1 chain, right? So this is a 1 chain with all coefficients 0. All right. For the figure on the right, okay, I hope you agree that C2 will include 0 and it will include this triangular face 1, 2, 3, right? So I hope you agree that there is just one triangular face for the figure for the simplicial complex on the left, right? So because of that, I hope you agree that C2 will be the vector space, okay, which includes this trivial 2 chain and this 2 chain which is 1, 2, 3. Is this okay? So this is what the C2 will be made up of. Now, if you look at Daba 2, right? So Daba 2 of 0, I hope you agree is 0, and Daba 2 of 1, 2, 3 is 1, 2 plus 1, 3 plus 2, 3. So you can see that in this case, image of Daba 2 includes both 0 and 1, 2 plus 1, 3 plus 2, 3. Is this okay? So now let's see how is this useful, right? So for the figure on the left and for the figure on the right, the kernels are the same. However, if you include the image of this Daba 2 operator along with the kernel information, then you will be able to see that yes, indeed, we can distinguish between the two cases, right? So the kernel and this image of Daba 2 together, you can see that are different to this pair over here for the second simplicial complex. So some way, if we can combine both these, the information that is present in both kernel of Daba 1 and image of Daba 2, I hope you agree that you will be able to distinguish between, a simplicial complex which has a hole and a simplicial complex which doesn't have a hole. Is this okay? So that is the genius observation, that just by looking at the elements of the kernel of Daba 1, we are not able to distinguish. However, if we additionally look at the image of Daba 2, then in this example, we would be able to distinguish between these two situations. In particular, for the figure on the left, there is something different, and for the simplicial complex on the right, something is different. And what is that something? The image of Daba 2 is different. Is this okay? So this is what is different. So combining this and this in some way, okay, I hope you agree that we should be able to count the number of holes carefully. Is this okay? So let me stop here for a few seconds. If you have any questions with regards to this discussion. So this was an intuitive discussion. Okay, we will now formalize this. but before we start formalizing, you should be able to appreciate what we are trying to do and why we are trying to do it, and then we will sort of discuss the formal details. Okay, so the formal details will be very algebraic in nature, so often it's not clear what is the motivation for doing all the things that we will now see. But if you understand this intuition, then the algebra will start making sense. Is this okay? So let me pause here for a couple of seconds. If you have any questions, please ask. All right, so surprisingly there are no raised hands, so maybe we can advance. All right. Okay, so we are now trying to formalize what we just discussed. Okay, so the general result that would be of use to us is what is referred to as the fundamental lemma of homology, right? And what is the fundamental lemma of homology? Well, this lemma, okay, is what is written in this red box over here, right? So see, it's a dream of every mathematician, and I presume it's a dream of every scientist, okay, that he wants to come up with these cute equations. So when I say cute, I mean something that can be written in very like in as few notations as possible, and write something that is very, very small in nature. I don't want to write an equation which is which is very complicated. I want to write such equations, right? So I hope you are able to appreciate that in this few symbols I'm able to sort of say the fundamental lemma of homology. Okay, so this is indeed, if someone asks you what is the fundamental lemma of homology, you can just say this, right? So now again you have to keep in mind that mathematicians on one hand are sloppy, right? But whenever they are sloppy, they ensure that there is no unambiguity, or there is no ambiguity in trying to decipher what they are trying to say, right? So here at first glance you may say, oh, okay, it looks very cute, but I don't understand what you are saying, right? What is this daba to the power 2 and so on and so forth, right? So it is not clear. So let's try to decipher this. As I said, while mathematicians may be sloppy, okay, if you sort of look at it very carefully, there will be an unambiguous way of deciphering it. Right, so typically when you write this, if there is an operator and it is there is something something like 2 that is written, often the interpretation is that you have to take some sense of a composition, right? So you have to sort of apply daba and you have to apply daba again. Okay, so that's what this daba to the power 2 represents, right? So let's try to see, just by looking at this equation, can we apply this daba twice, right? So if I ask you this question, okay, do you think I can apply daba p twice? What would your answer be? Can one of you volunteer and tell me, can I apply daba p back to back? Can one of you please volunteer? Yes, Abhishek, go ahead.
That domain is different, so we cannot.
Very good, thank you. Okay, so that's a very short and correct answer. Okay, so you cannot apply daba p back to back, right? So why can we not apply? So recall that the domain of daba p is cp and the codomain of daba p is cp minus 1, right? So which means that if you give some p chain as input to daba p, the output of this daba p application would be a p minus 1 chain. Now once you have a p minus 1 chain, you cannot apply daba p again, right? So clearly you cannot interpret this daba raised to 2 as daba p applied twice, right? It just doesn't make sense. Okay, so what is the next best interpretation? Well, the next best interpretation is that you first apply daba p, or for simplicity, let's say daba p plus 1. So daba p plus 1 goes from cp plus 1 to cp, and whatever is the output on that, you apply daba p, right? So I hope you agree that this daba raised to 2 can be interpreted as daba p, okay, composed with daba p plus 1. So I hope you agree that this operator goes from cp plus 1 to cp minus 1. Is this okay? So this daba p plus 1, if you give a p plus 1 chain as input to it, the daba p plus 1 will give you a p chain, and on that the daba p operator can be applied, and whatever you apply, the output of this DABA P operator will be a P minus 1 chain. So that's what I have written over here, that for the composition of these operators, okay, you give something as input in the P plus 1, the input is a P plus 1 chain and the output is a P minus 1 chain. Right, so after a little bit of trial and error, you will be able to see that this DABA2 can only imply this composition of operators. So this thing, since you have written this identically equal to 0, it should mean that this should be true for all P. So whatever P you take, if you take the composition of these DABA P operators in the following way, right, this should be identically equal to 0, which means that whatever P plus 1 chain you give as input to this composition of operators, the output will be 0, and this 0 will be the P minus 1 chain. That is, it will be the additive identity in CP minus 1. Right. So the fundamental level of homology means the following. Okay, you give me any P, right? So let P be any integer, right? So let P be any integer. You fix an arbitrary P plus 1 chain and you apply these DABA operators sequentially. That is, you first apply the DABA P plus 1 operator, whatever is the output, on that you apply this DABA P operator. The claim is that this will always be 0. Is this okay? So this is the interpretation of this fundamental lemma of homology. So you can see that one can write it in this 1-inch block, right? This simple lemma, and if you sort of expand on a bit by carefully making sure that there are no trivial issues, so you can see that this cannot be interpreted as composition of DABA P with itself. Hence, it should mean the composition of DABA P with the DABA P plus 1, right? So once you interpret that, you will be able to see that this short 1-inch equation indeed represents something like this. So this is the fundamental lemma of homology. So I have written it in an algebraic sense. Okay, what I claim is that this statement can be equivalently interpreted as meaning or referring to this equation. Okay, so I am claiming that this equation over here can be equivalently interpreted as saying the following. Right, so what is the equivalent statement? That the image of DABA P plus 1 is a subset of kernel of DABA P. Okay, so can one of you help me figure out why this relation and why this relation are one and the same? Can one of you please help me? Why is this equation and this equation one and the same? Yes, Jacob, please go ahead.
DABA P plus 1 of C gives rise to the set or image of DABA P plus 1.
So let's just interpret what you said, right? So what is image of DABA P plus 1, right? So this is all those chains, okay? So chains, let's call it C prime in CP such that there exists C in CP plus 1 with DABA P plus 1 of C equals C prime. Do you agree?
Yes.
So now, okay, so this is what image of DABA P plus 1 is. Okay, please go ahead with your explanation.
And kernel of DABA P is C dash C in CP.
Such that DABA P
is mapped to 0 in,
right? DABA P of C is 0. This is what the kernel of DABA P means, right? Do you agree?
Yes.
Right? So now what we are saying is that whatever C you give as input to DABA P plus 1, whatever is the output of this operation, I hope you agree that by taking every possible C, we would be able to cover every element in the image of DABA P plus 1. You give that as input to DABA P. And we are claiming that if you give any element in the image of DABA P plus 1 as input to DABA P, okay, the output will be 0. So I hope you were able to see that this statement and this statement are one and the same. Okay, so again, I'll pause for a few seconds. If any one of you has questions why these two statements are one and the same, this may be a good point to ask. All right, so I don't see any raised hands, so let us just advance. Okay, so we are going to show that this is a subset of this, right? So in particular, we want to show that for every C in CP plus 1, this relationship actually holds true, right? So let's try to recall what this CP plus 1 is. So CP plus 1 is summation AI sigma I over I such that AI belongs to Z2 and sigma I belongs to F P plus 1 of delta. Okay, this is what your CP plus 1 is, and we have shown that this CP plus 1 is a vector space. That is what we have shown. Furthermore, we have shown that one basis for CP plus 1 is this set. Okay, sigma 1, sigma 2, all the way up till sigma FP plus 1. Right. So recall what this little FP plus 1 is. This equals the cardinality of FP plus 1 of delta. Okay, so this is something we have already seen. Again, you have to appreciate when I write sigma 1, sigma 2 here, right? This has to be interpreted as the this P plus 1 chain where you have 1 in front of sigma 1. So this should be 1 sigma 1, right, plus 0 sigma 2 plus blah 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 plus 0 sigma fp plus 1. See, I'm I understand that I'm repeatedly sort of emphasizing on these minor things, but this is based on my previous experience that when I write sigma 1, people interpret this as referring to the set sigma 1, right? That is not the case. When we write it as the CP plus 1 vector space, you have to implicitly recall that CP plus 1 is made up of chains, right? So this cannot just mean the set, it has to mean this P plus 1 chain over here. So although I write it as sigma 1, I am being sloppy, but there is an unambiguous way to decipher what this thing means, and that's why I'm repeatedly saying this, because over a period of time we will just write these notations, but even at that time you should at the back of your mind realize what is being said. Okay, you shouldn't just blindly say that, oh, since it's sigma 1 it's a set. No, it is not a set, it refers to this P plus 1 chain. All right, okay, so let's go back to what we were trying to do. We were trying to prove this fundamental lemma of homology. Okay, and in order to prove that, we first recall that this CP plus 1 is this vector space, and sigma 1, sigma 2 all the way up till sigma fp plus 1, these this collection of P plus 1 chains forms a basis for CP plus 1, right? So keeping this in mind, what we do is we are going to sort of first prove this result over here. Instead of trying to prove it for generic C, we will first prove it for the basis elements. Is that okay? We will first prove it for some basis element. So instead of proving it for any generic P plus 1 chain, we will prove it for the basis element. So let's pick some arbitrary sigma I and let me call this as sigma. Okay, so this sigma over here represents an arbitrary basis element in this choice of basis. Is this okay? So let sigma be some P plus 1 phase. And when I write this sigma over here, you have to interpret this as the P plus 1 chain, right? And our goal now is to show that dabba P of dabba P plus 1 of sigma is 0. Is this okay? So that is what our goal is. So let's try to prove this. Okay, so since sigma is a P plus 1 phase, I hope you agree that it should have P plus 2 vertices, right? So keeping this in mind, I assume that the vertices of sigma are denoted by V0 all the way up till Vp plus 1. So since there is V0 over here, I hope you agree that the total number of vertices in sigma is P plus 2. Right? Now if I apply this dabba P plus 1 operator on sigma, I hope you agree that I will end up with this sum over here. The sum on the right, I hope you agree, is a P chain. It is a P chain because it's a formal sum of P faces. It's a P chain because it's a formal sum of P faces. And what are the different P faces? Well, the P faces are those faces obtained from sigma by dropping one of its vertices at a time, right? So you start from 0, you go all the way up till P plus 1 and you keep dropping one of the vertices and you end up with this P chain. Is this okay? So I hope you agree that dabba P plus 1 of sigma is this, right? So we want to show that whatever is this output, on that if you apply this dabba P operator, the output will be 0. Okay, so that is what we are interested in showing, right? So my first claim is that if you apply dabba p on dabba p plus 1 sigma, and since dabba p plus 1 sigma is this sum, right, dabba p of this must be sum of dabba p of this, right? So can one of you explain why I could take dabba p from outside the sum to inside the sum? Can one of you justify this step over here? Why could I take dabba p inside the sum? Because on the left, I hope you agree, I have dabba p of summation j equals 0 to p plus 1 v0 vj hat blah 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 vp plus 1. So can one of you tell me how could I take this dabba p inside the summation? Yes, Jacob, please go ahead.
I think dabba p is a linear operator.
Very good. Okay, so it's a vector space homomorphism, or it's a linear operator, right? So you are giving a sum of elements, okay, as input to this dabba p operator. So you know, the dabba p, since it's a linear operator, the output of this would be the sum of the corresponding outputs. Okay, so that's what I have written over here. All right. So now I am going to apply dabba p on this, you know, on this p face, right, or the p chain corresponding to this p face. So as you can see, this has p plus 1 vertices, right? So why does it has p plus 1 vertices? Well, the original face had p plus 2 vertices, and this vj hat over here means that some vertex has been dropped. So from the p plus 2 vertices that we originally had, after dropping one vertex, we are left with only p plus 1 vertices. Okay, so this is a p face, and now I am going to apply dabba p on that, right? And I hope you agree that after you apply dabba p, we will end up with a face where both the ith vertex and the jth vertex are dropped, right? And now I claim that this sum must be 0. Can one of you tell me why is this sum 0? What should your, why do you think this sum is actually 0? Can one of you think a bit and tell me why is this sum 0? Would one of you like to volunteer? Why do you think this sum is 0? Yes, Agnit, go ahead.
Sir, each term would appear twice.
Okay, very good. Why do you think each term will appear twice? So let's take an example. Okay, so since this is just in notations, it may be a bit complicated. So let's take a three phase. Okay, so three phase meaning this is a three chain in C3. Okay, so let's take this three chain 0, 1, 2, and 3. Right, so now I'm going to apply dabba 2 on it. So what would be the output of this? Agnit, can you help me?
Yeah. So, sir, this is a three phase, right?
Yeah. So this is a three phase because it has 4 vertices, right? It's a three-dimensional phase. Now
Yeah,
I'm
right.
applying dabba 3 on it. Sorry. It should,
Yeah,
yeah.
Okay, yeah, that's why I was confused. Okay,
Yeah.
so it would be 0, 1, 2 plus
Yes.
1, 2, 3.
How about you go step by step? Like
Okay.
you drop one vertex in order, right? So you drop the third vertex. Now let's drop this. You drop the fourth vertex. Let's drop the third vertex. Then.
Okay. Then
0,
you go 0, 2, 3. Yeah.
And 1, 2, 3.
1, 2, 3.
Okay, so this is the output of applying dabba 3. Now I have applied dabba 2 on whatever is this, right? So what will I end up with? So if I apply dabba 2 on 0, 1, 2, so I hope you agree that since dabba 2 is a linear operator, if I apply dabba 2 on the above thing, I'll end up with something like this. Okay, plus dabba 2 1, 2, 3. Okay. So now if I apply DABA2, so let's go over it one by one. So I'll write it in short. So 0, 1, 1, 2 plus 0, 2, and then I will end up with 0, 1 plus 0, 3 plus 1, 3, and then I'll end up with 0, 2 plus 0, 3 plus 2, 3, and then I'll finally end up with 1, 2 plus 1, sorry, what am I doing? 1, 2 plus 1, 3 plus 2, 3. Right, so this is what I'll end up with, and as you can see, right, this will cancel with this, and this 1, 2 will cancel off with this 1, 2, this 0, 2 will cancel off with this 0, 2, and then this 0, 3 will cancel off with this 0, 3, and this 1, 3 will cancel off with this, and this 2, 3 will cancel off with this. So you can see that every phase is appearing twice in this sum that we have over here, and that's why it cancels off, right? So I will leave it as an exercise for you to think, why does every p minus 1 phase that you end up with appear twice in this sum, right? So this is not very difficult to see why that is the case. So I encourage you to think a bit about it, and it is because of this reason that we end up with 0. Is this okay? So it is because of this reason that we end up with 0. So what have we managed to show? Our goal originally was, right? Our goal originally was to show that for any C in CP plus 1, this relationship holds, right? So what have we managed to show? We have managed to show that you give me any P plus 1 phase, this above relation actually holds true, right? So now I am claiming that the proof is done. Can one of you help me figure out why is the proof done? So this is what we had to show, right? For every C in this, we managed to show that this is true, and now I am claiming that the proof is done. Why do you think the proof is done? Why do you think the proof is done? Yes, Jacob?
Every C can be represented as some combination of the basis elements. So
very good. So what?
So if I take an arbitrary C, it can be expressed as some linear combination of.
Okay, so let's just think about it, right? So what you are saying is that let's take an arbitrary C. So this can be interpreted as summation AI dot sigma I. Okay, then what?
Then since DABA P is linear.
So DABA P plus 1 is linear and DABA P is linear. So what? What about composition of linear operators? Is it also linear?
Yes.
Okay, so this is a theorem that we proved in the linear algebra class, that the composition of linear operators is also linear. Is this okay? So this composition, it's itself a linear operator, right? So this goes from Cp plus 1 to Cp minus 1, and we have a basis for Cp plus 1, and on every basis element, this operator, maps it to 0, right? So if you give a linear combination of inputs to this linear operator over here, the output will be summation I AI DABA P of DABA P plus 1 of this sigma I, right? So since this is 0, this will be summation AI dot 0, and that's why the output will be 0. Is this okay? So I hope this proof is clear. If you have any questions, please ask. Okay, one more thing. See, I have sort of put a scalar multiplication sign over here, but if you sort of recall, we say that any C, I can write it as this summation Ci sigma I, right? So I'm saying that this representation and this representation, okay, are, the way we write it or way we interpret it is different, but they are one and the same. So why is that? Because each sigma I you can interpret as 0 sigma 1, this formal sum 0 sigma 1 plus 0 sigma 2 plus dot 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 plus 1 sigma I plus dot 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 0 sigma f p plus 1, right? So you can interpret it in this fashion, right? So a sigma I, okay, this one chain, you can interpret it as a dot sigma I, where this sigma I is actually representing this one, this p plus 1 chain. So a sigma I, right? You can also interpret it in this fashion when you enter. So in that sense, A1 sigma 1, the formal sum A1 sigma 1, A2 sigma 2 plus blah 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 plus A F P plus 1 sigma F P plus 1. This you can also interpret it as A dot sigma 1 plus blah 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 A F P plus 1 scalar product sigma F P plus 1. Right. So the difference between what I have written on the left and what I have written on the right is that on the left I have a formal sum, on the right I have Fp plus 1 formal sums, right? These are the formal sums corresponding to this individual p plus 1 phase, and I'm looking at the linear combination. Okay, so this I think should be A1, right? So these two things are one and the same. Okay, so it is important to be able to write it in the second way. So I can interpret this formal sum as a linear combination of these different p plus 1 chains, right? So I can interpret the thing on the right, okay, as a linear combination of this p plus 1 chains, and then I can, you know, sort of imagine that this daba p composed with daba p plus 1, this is a linear operator. So if I give a linear combination of inputs as input to this operator, the output would be a linear combination of the corresponding outputs. Now this is something we have already shown is 0, hence this entire thing will be 0. Is this okay? So I hope you agree that you know, we managed to show that this image of daba p plus 1 is indeed a subset of kernel of daba p. Okay, so let me pause over here. Okay, if you have any questions, this may be a good time to ask. Do you have any questions with the statement of the lemma and its proof? See, I cannot see your faces or, you know, how you are interpreting. So there is no way I can know whether you have understood something or not. If you have not understood, please, you know, make some effort to raise your hand and ask questions. Okay, there is no way I can understand whether you have understood it or not. Okay, so please volunteer and let me know if you have not understood something. All right. Okay, so I don't see any raised hands, so maybe we can continue, right? So if you recall, okay, we sort of gave a special symbol to the kernel of daba p, right? So we said that we will use this symbol z subscript p to denote the kernel of daba p. Similarly, we will you know, give a special notation for the image of daba p plus 1, right? So the image of daba p plus 1, okay, this is, we will denote it as bp, right? B subscript p, okay, and the b subscript b over here is used to denote boundary. Okay, so and we will refer to the elements of this bp, which is the image of daba p plus 1, as a p boundary, right? So the p boundary is supposed to mean that it is the boundary of some p plus 1 chain, right? So it need not be just one phase, right? What we are saying is that you take, so image of daba p plus 1, I hope you agree, is the output when you apply daba p plus 1 on a p plus 1 chain, right? So this elements of bp basically consists everything that can be interpreted as the output of daba p plus 1 when it is applied on a p plus 1 chain. So this is the collection of all possible outputs. Is this okay? And we have shown that image of daba p plus 1 is a subset of kernel of daba p, right? And in one of your exercises in assignment 1, okay, you were asked to show that if you have two groups, let's say G to H, right, and let's say you had a group homomorphism, right, and you were asked to show that H of G is a subgroup of H, right? So the image of G under little h is a subgroup of H. So this is something you were asked to show, right? So in similar spirit, what I am claiming is that in similar spirit, observe that you know, you have this CP plus 1 here, right? You have a vector space homomorphism between CP plus 1 and CP, right? So let me just emphasize what is happening. So you have CP plus 1 and you have this daba p which goes to CP, right? So we know that this daba p is actually a vector space homomorphism, right? So the image of this, right? So the image of this that is daba, sorry, I should have daba p plus 1 here, sorry about that. So daba p plus 1 goes from Cp plus 1 to Cp. So the image of daba p plus 1, right, this will be a subspace of Cp, right? This will be a subspace of Cp. What does this mean? This means that this image of daba p plus 1 is a vector space in itself, right? It's a vector space and it is a subset of Cp. Okay, so this you can prove in the same way you proved your assignment exercise. So if you recall, you showed that if G and H are two groups, if you look at the image of a group homomorphism, right, then the image of a group homomorphism is a subgroup of H, right? So in the same way, here we are dealing with vector space homomorphisms, right? So if you look at the image of a vector space homomorphism, that one will be able to prove that it is a subspace of Cp, right? So in other words, this one can think of as a vector space in itself, right? So this is a vector space in itself, right? So let's try to interpret what is happening. So let's try to see what are the different objects of interest for us from the perspective of homology. On the left, you have Cp plus 1. So this is a vector space. On in between, you have Cp. This is another vector space. And on the extreme right, you have Cp minus 1, which is another vector space, right? So between Cp plus 1 and Cp, you have this daba p plus 1 operator, and between Cp and Cp minus 1, you have this daba p operator. Okay, so far so good. So now, what is this green region over here? Okay, so this green region over here is the image of daba p plus 1, right? So the filled green region is the image of daba p plus 1. So as you can notice, this green region is drawn as a subset of Cp, right? Because the image of daba p plus 1 will indeed be a subset of Cp. But what we also know is that this image of daba p plus 1 is also a subset of kernel of daba p, right? So what I have now drawn is this red region over here corresponds to the kernel of daba p, right? So what is the kernel of daba p? It is all those elements in Cp that get mapped to the 0 in Cp minus 1, right? So all the p chains in this region, okay, they get mapped to 0 under daba p. So these elements over here correspond to kernel of daba p, right? And we have already shown that image of daba p plus 1 is a subset of kernel of daba p, right? So that's why the green region is drawn as a subset of the red region. Is this okay? And since this is a vector space in itself, and this is a subset of kernel of daba p, and in one of your exercises you must have also seen that the kernel of a group homomorphism is a subgroup, right? So in the same way, you can see that the kernel of daba p is actually a vector space in itself, right? So what is happening? So let me summarize. Okay, so all the action is happening at Cp. So Cp is this big vector space. Within that, there is this kernel of daba p. This is another vector space. So in fact, this is a subspace of Cp. And in addition to that, within kernel of daba p is the image of dp plus 1 or daba p plus 1. So this is another vector space, right? So this is a subspace of kernel of daba p, which itself is a subspace of Cp. So you have these three subspaces, okay, which are which satisfy this sequential property that Bp, which is the set of all p boundaries, is a subset of Zp, which is the set of all p cycles, which itself is a subset of Cp, okay, which is the set of all p chains. Okay, so this is what we have managed to prove. Okay, so the fundamental lemma of homology shows that Bp is a subset of Zp is a subset of Cp. Is this okay, right? And why is this Bp of interest to us? This Bp is of interest to us. Notice that Bp is a subset of Zp, so every element in Bp is also a p cycle. However, the elements in Bp are in some sense the the uninteresting stuff in kernel of daba p. So let me again repeat. Kernel of daba p, we realized, contains p cycles. So what are these p cycles? These are those p chains which daba p takes to 0, right? So this is useful for us because it helps us figure out if there are these hollow regions or not. However, we realize that just by looking at the kernel of DABA P, one will not be able to distinguish between a hollow region and a filled region, right? So to tackle that problem, we sort of realize that, okay, all these filled regions in some sense can be determined by looking at the image of DABA P plus 1. Right, so the image of DABA P plus 1 is precisely BP, and so the point is this: every P chain in BP is a P cycle, okay, which means that if you apply DABA P on that, it will be mapped to 0. Okay, so every P chain C in BP is a P cycle, that is DABA P of C will be 0, right? But it is or it represents filled regions. Okay, it represents filled P cycles. Is this okay? So this is the interpretation of BP, right? So what we want to do is, we want to count the elements in ZP, but we want to ignore the elements in BP. This is what our goal is. How we do it, we will discuss it, but this is the intuition, right? That ZP contains this interesting stuff, but also some non-interesting stuff. But the good thing is, the non-interesting stuff can be captured by or represented by the elements in BP, right? So we want to somehow count the elements in ZP by ignoring the elements in BP. Is this okay? That's what our goal is. And one way to do this is via this quotient operation, right? So finally, we are there at the pth homology group. So what is the pth homology group? It is the quotient of ZP with BP, right? So if you had some algebraic background, you will be able to immediately decipher why we are doing this quotient operation, right? Because we want to somehow ignore these elements in BP and only focus on elements that are there in ZP. And I'm claiming that by using the quotient operation, okay, we are actually able to do this. Is this okay? And now I can define the pth Betti number, right? So this is denoted by Betti P. So this is named to appreciate the contributions of this mathematician called Enrico Betti. Right, so the Betti number is named after this mathematician by the name Enrico Betti. He was the one, as far as I understand, who sort of helped define this sequence of homology groups and so on and so forth. Right, so let's understand what this Betti P is. Well, ZP is a vector space, BP is a vector space, right, and this is a subspace of ZP. So we can take the quotient operation, and in you will be able to show that, we were able to actually show that, by taking the quotient operation, we end up with another vector space. So quotienting of two vector spaces gives rise to a natural vector space, and that is what we denote by HP, right? And since HP is a vector space, we can talk about its dimension, and whatever is the dimension of this vector space, okay, so that is what is represented by the pth Betti number, which is beta subscript p, right? So algebraically we sort of know what is beta p, right? So beta p is the dimension of this vector space HP, right? So this is what we are trying to do. So now I have given you the definition of what the pth Betti number is, and from now on, okay, so notice that this is the dimension. Okay, so now I can define what a p hole is, okay, or the number of p holes, which is equivalent to the number of p plus 1 dimensional holes. Okay, so this is equal to the number of independent or number of, I shouldn't say independent, number of elements in the basis of HP. Okay, so this is what beta p is. So beta p equals the number of p holes, okay, and this equals the number of p plus 1 dimensional holes, right, and this is equal to the number of elements in the basis of HP, right? So I'm just giving an interpretation of what the dimension of a vector space means. Well, it's the number of elements in the basis. So that's all is what is written over here. So why it is useful and so on and so forth, that will be the the discussion that we will be having now. But at the beginning of this class, I said we would be able to count the number of holes of different dimensions. I have given you the recipe to compute. Okay, now why is this recipe useful? Is it possible to compute it? All those things is the discussion for that will happen henceforth. Is this okay? But this is the definition, and you have to appreciate that this is something that is well defined. So let me pause here for a second or two. If you have any questions, with regards to the definition, we will discuss them now. Okay, the intricacies and so on and so forth, it will become clear when we sort of look at different examples and so on and so forth. It will become clear to you why are we taking this quotient operation and so on and so forth. Okay, so let me know if you have any questions. Okay, so Ichit, do you want to unmute yourself and ask? You have posted a question in the comments, but would you like to unmute yourself? Ichit? Okay, no problem. Okay, so so those who want to know, he has posted a question in this chat. So if you want, you can see that. So he says that 0 belongs to BP and hence 0 does not belong to HP. So I don't know why you claim that. So that is not true. Okay, so quotienting does not mean that we remove some elements from remove certain elements. Okay, so we define some equivalence classes, right? So quotienting means that we define an equivalence relation and we combine some elements, and we sort of instead of looking at these different elements separately, all similar elements, we will look at them as one and the same, right? So a loose interpretation of quotient is that BP has so let's try to interpret. So here is ZP, here is BP, right? So this is BP and this bigger set is ZP. So the quotienting operation, what does it mean, right? So what it means is that, let me first give the formal interpretation. So HP is ZP quotient BP. So this means that you have to look at all the equivalence classes of X in ZP. And what is the equivalence classes? Well, the equivalence class of X, which is an element in ZP, is all Y in ZP such that Y minus X lies in BP, right? So this is the formal interpretation, right? So I mean, when you say that 0 does not belong to HP, okay, you have to tell me that there is no element in this set that that can behave like the additive identity. Is this okay? So my claim is that that is not true. We will in fact be able to show that if ZP is a vector space and BP is a subspace of ZP, whenever you take the quotient operation, you will end up with something like this, and this collection will indeed have an element that behaves like the additive identity. Okay, so your claim is not true that 0 belongs to BP and hence 0 does not belong to HP. Okay, so that claim is not true, hence the subsequent statement of yours is also not true, right? So first, so this is the formal description of how you do the quotient operation. Okay, so now let me try to give an intuitive interpretation of what do we do that what do we mean by taking the quotient operation. Right, so BP is a vector space. So maybe I'll draw a bigger figure so that I can draw inside few things inside it. So let's say this is ZP and let's say this is BP. So what is the idea? So we are saying that BP is a vector space, so it will have a 0 within it, right? So in the quotient operation, what we are saying is that we will think every element in BP as 0, right? So the loose interpretation of quotienting operation is that every element in BP is to be interpreted as 0, right? So what we are saying is that all these elements, whenever we are taking the quotient with BP, all the elements in BP, we will think of them as being one and the same, and we will interpret it as 0. So let me now try to prove why that is the correct interpretation, right? So my claim is that I hope you agree that 0 belongs to BP, since BP is a vector space, and 0 also belongs to ZP. Right? So one can ask, in this collection, what is the equivalence class of 0? So my claim is that the equivalence class of 0 is actually BP. Right? So let me prove that. So in order to show that the equivalence class of 0 is BP, I have to show that every element for all C in BP, right? C0 is equivalent to C, right? So this is what I need to show in order to prove this statement. And in order to prove this, I have to show that C minus 0 actually lies in BP, right? So if you sort of recall the definition of this equivalence class, right? So we will say two elements X and Y are equivalent if their difference lies in BP, right? This is what this quotienting operation means. So in order to show that 0 is equivalent to any element C in BP, I have to show that C minus 0 is actually in BP. But C is in BP, 0 is in BP, right? Because BP is a vector space, C and 0 both are in BP, so the difference must also be in BP, right? So trivially, C minus 0 is C, and this trivially belongs to BP. So from this, it follows that indeed the 0 is equivalent to every element in BP. So what it means is that is exactly what I said over here. When you quotient with some subspace, what you are saying is that we will sort of set all the elements in this subset as 0, right? So this will be the equivalent, the set of elements that are equivalent to 0, and one would be able to show that this is an element in HP, and this will play the role of the additive identity in this new vector space. Is this okay? So Ichit, I hope you are able to appreciate what I'm trying to say, that every element in BP we are saying are equivalent, okay, and we will denote this in the equivalence class of any element in BP as the new 0 element, or the equivalence class of 0, and this will play the role of the additive identity in HP. Is this okay? So let me pause here for a second or two. If there are any questions, please ask. Please ask if you have any questions. Please don't hesitate. It's a bit surprising that nobody has any questions. I thought I would have many people asking questions at this point, but it's surprising. Either each one of you knows this stuff, or most of you are a bit lost, but nevertheless are very, very hesitant. Okay, this is not a good attitude to have. If you have questions, ask. Don't think that you are the only one who is not understanding, and so on and so forth. Okay, please don't hesitate. Please ask. All right, so I don't see any raised hands. So maybe we will look at a bunch of examples, okay, to sort of appreciate what this Betty numbers, try to do and how we can compute them, right? So I have not told you how Betty number is actually helpful in looking at the number of these p plus 1 dimensional holes. But this is something that we will sort of try to appreciate through some examples to how we compute this, and slowly you will be able to see why this Betty number is actually able to count these different holes. Okay, so to begin with, we will look at a very, very simple example. So the purpose of this example is to make sure you understand how to do these different calculations. Okay, that's the purpose, and hopefully in the next class we will do a slightly more complicated example, and with that you will be able to see or you will be able to figure out in general, if any simplicial complex is given to you, how to go about computing the different Betty numbers corresponding to that. All right, okay, so here is a simplicial complex. Okay, so this is a simple simplicial complex. It is simple in the sense that it has just two vertices, that's it. Okay, it has no edge, it has no triangle, nothing. It just has two vertices. Now let's try to compute the Betty numbers of different dimension corresponding to this simplicial complex, right? So if I ask you how many holes are there of different dimensions, what would your guess be? Right, so clearly it has no interesting cycles and things like that. So your guess will be that all Betty numbers will be 0. Okay, so that would be your guess, but it is not clear what Betty zero should be, right? So because we don't know what is the notion of a zero cycle, right? Because we can understand, sorry, we don't understand what's the notion of this zero hole, right? So when I say, what is a one hole, you'll be able to draw figure like this. Maybe you'll be able to draw some figure like this, right? So all these represent one holes or two-dimensional holes. Right, so these are all two-dimensional holes. But if I ask you what is a zero hole or what is a one-dimensional hole, right? So to begin with, it's unclear because this is not something that we have seen in our school, or it's also difficult to interpret, right? But nevertheless, the idea is that if we follow the same procedure that we followed for higher dimensional holes, okay, the same computation will help us figure out what a zero hole or a one-dimensional hole actually means. All right, so let's just blindly compute the Betty numbers corresponding to this simplicial complex. Okay, so again I repeat that this simplicial complex has two vertices, and consequently if you sort of look at the zeroth, the set of zero chain, that is the C0 vector space, I hope you agree that it will contain V1, V2, V1 plus V2 and 0, right? So these will be the four elements that will be there in C0. Now since there are no higher dimensional faces, right, CP will be 0 for all P not equal to 0. Okay, I would also like to stress that we are going to first compute these Betty numbers. Sorry, I would also like to stress that we are going to first compute these Betty numbers, assuming that we are going to work with the usual homology setup. Okay, so because we are working with the usual homology setup, C minus 1 is the trivial vector space, and consequently CP will be the trivial vector space for all P not equal to 0. Right. So now let's compute, the pth homology group for every P. Right. So to begin with, let's consider the case where P is bigger than equal to 2. Right. So since P is bigger than equal to 2, CP plus 1. Okay, P plus 1 will be bigger than equal to 3, and because of this relation, I hope you agree that CP plus 1, CP and CP minus 1, all these three vector spaces will all be the trivial vector space. Okay, so they will all be the trivial vector space. So consequently, what you have is, here is CP plus 1. It only includes one element, which we will call the additive identity. Similarly, CP also has only one element, which is the additive identity, and CP minus 1 also has only one element, which has the additive identity. Right? So in this case, I hope you agree that daba P plus 1 of 0 will be 0, and daba P of 0 will be 0. So if you look at ZP over here, this will only include the 0 element, and similarly BP over here will only include the 0 element, right? So the only element over here which is mapped from 0 is 0 itself. So you can see that ZP and BP are 0, right? So this is what we have managed to show, that for every P, when both CP plus 1, CP and CP minus 1, all of these, if they are trivial, then CP, ZP and BP, they all must be one and the same. That is, they all must be including only the trivial, like the additive identity, right? So in this case, let's try to compute the quotient of ZP with BP, right? So HP, so what is this? Well, this is the collection of all equivalence classes, okay, where its representatives lie in ZP, right? This is the formal definition, right? And what is the equivalence class of X? The formal definition is the collection of all Y in ZP, which is equivalent to X, right? And if you remember, when we talked about this quotient space definition, we said that two elements are equivalent if their difference lies in BP, right? So this is how we had defined. So let's try to compute HP in this scenario, that is CP equals ZP equals BP equals 0. So since there is only one element in ZP, okay, trivially HP will only include the equivalence class of 0. Right? So what is the equivalence class of 0? Well, the equivalence class of 0 is the set of all elements that are equivalent to 0. Right? So my claim is that the set of equivalent elements to 0 is only 0. And why is that? Well, this is because 0 is equivalent to 0, because 0 minus 0, which is 0, this lies in BP. So I'm just verifying this property over here. Hence, HP is made up of the equivalence class of 0, and the equivalence class of 0 is actually a set which only includes 0. Is this okay? And you recall, the way we had defined the addition operation on the quotient space was the following. So since there is only one element, we only have to do the addition of this element with itself. So the way you add is, you take this equivalence class, add it to this equivalence class. So what is the output of this? Well, you take the representative element, add them together. Whatever is the output, take its representative class, take its equivalence class. That equivalence class will be the output of the sum of these two equivalence classes. Is this okay? So take this equivalence class, take this equivalence class. If you want to add them up, the way to do it is, you take these representatives, add them up. Whatever is the output, look at the equivalence class corresponding to that. That equivalence class will be the output of this. So in this specific example, the addition of this equivalence class and this equivalence class is simple, because 0 plus 0 is 0, hence you will end up with 0. So you can see that this element belongs to HP, this element belongs to HP, and if you add them up, you will end up with another element that belongs to HP itself. And similarly, you can define this scalar multiplication. Again, if you recall the rule of scalar multiplication, so these two are elements in Z2, right? So these two are elements in Z2. So these two are elements in Z2. So you take 0, the scalar multiplication with an element in this quotient space is defined in the following way. You first do this scalar multiplication inside, you will get some value which is 0, and you look at the equivalence class corresponding to 0. So this is the output of this scalar multiplication. Similarly, the output of this scalar multiplication is the equivalence class equivalence class corresponding to one scalar multiplication 0, right? So this is 0 itself, and hence you end up with this equivalence class. So you can see that the output of this addition is an element in HP. Similarly, the output of this scalar multiplication is an element in HP itself. Okay, so in that sense, you can see that HP is a Z2 vector space, right? So HP is a Z2 vector space. Is a Z2 vector space. By that I mean that it is a vector space over the field Z2, right? So this is a Z2 vector space, and it only includes this element, and you can see that it behaves like an additive identity. So you can see that HP can be viewed as a trivial vector space because it only includes the additive identity. That's all, right? So one of you can ask, well, is HP equal to CP, right? So if you remember, CP also was this trivial vector space. It only included this additive identity, right? So if I ask you this question, is HP equal to CP? Well, the answer to that would be that no, HP and CP are not the same, right? However, they are isomorphic, right? They are not one and the same because the element that is there in HP is not the same element that is there in CP. In CP, you have an element. In HP, you have an equivalence class of this element. Is this okay? So, the way we write it and so on, it may appear it's one and the same. It's not one and the same because what is there in HP is the equivalence class. So, it is a set, right? Whereas here you only have an element. So, 0 is an element in CP, whereas in HP, okay, you have the element of HP is the set containing 0. Okay, so there is some subtle difference. So because of this reason, HP and CP are not one and the same. However, they are isomorphic. Both of them are trivial vector spaces. Okay, and since this is trivial vector space, from this one can conclude that indeed the pth Betti number is 0 for all p bigger than or equal to 2. And in the same way, for p less than -2, one can conclude that beta p is 0. Right, so in the same way, because all these CPs will be 0, so beta p will be 0. So it remains to compute the pth Betti number for these coefficients, and this would be a discussion for the next class. So maybe this is a good place to stop. Let me stop recording.